Hello, everyone, and welcome to today's webinar. I'm Robin Carr, and I'll be your moderator for today's event. Thanks for being here. Before we get started, I have a few housekeeping items to go over. If you lose audio or visuals, simply exit GoToWebinar and come back in to restore your connection. The chat feature available in your GoToWebinar menu panel should only be used for general comments or technical assistance. If you have a question for our speaker, please put your questions in the questions section of your GoToWebinar menu panel as you think of them. And at the end of the presentation, I'll have an opportunity to ask Michael your questions. The handout section of your GoToWebinar menu contains a PDF version of today's presentation deck, and you can download that at any time during today's event. The presentation is being recorded and will be available on our Fluke YouTube channel within a few business days. We'll hear from our speaker, Michael DeMaria, if I can talk today, and then we'll go into our Q&A session and we'll answer as many questions as we can. Michael is a director of Azima DLI Product Management, managing the hardware platforms and integrations, diagnostic software and AI tools, and user portal deliverables and business metrics. Michael's background is in the Navy, nuclear engineering, but has also been working in vibration for over 30 years and managing key accounts, technical support, customer training, and product management for Azima DLI since 1995. Again, our speaker today is Michael DeMaria, and Michael is speaking about reliable assets in resource constraint economy. Michael, take it away.
Great, thank you, Robin, and welcome to you all. So yeah, as Robin said, today's talk is really going to be about how we move forward today in where customers are really facing constraints in their labor, staff, and the resources that they need in order to do condition-based maintenance. So if you aren't familiar with this, Azima DLI is a global leader in vibration diagnostic automation and professional analysis services. We use AI-enabled advanced software technologies, and we apply that application to automatically identify early component level machinery faults and present prioritized actionable repair recommendations. We have about 50 years of professional experience and an AI engine that's been trained for the last 30 years with about 100 trillion data points. So our analysts are about 5 times more efficient in their utilization rate for doing analysis. We'll talk quite a bit about this as we talk through the resource constraints as customers are facing. As Robin pointed out, I am the product manager for Azima DLI. I've had lots of roles within the company over the last 30 years. I actually started as a customer to DLI back in 1988 as I managed the entire vibration analysis program on board one of the aircraft carriers. And then that led me to, since DLI Engineering had that contract for managing all the aircraft carriers, as soon as I joined the company in 1995, that was my very first task. So I took the leadership role in managing the entire aircraft carrier program for all the ships, and that led to really a great understanding about how remote condition monitoring, utilizing staff that is constantly churning, operators that have technical limitations on the understanding about vibration analysis from an analytical perspective, whereas the plants are really kind of focused on maintaining what they do and not necessarily trying to learn new technology, which is really kind of challenging. And the same applies to today. Plants have a hard time keeping staff, and how do you utilize technology in a way that enables those constraints and as a solution. The Navy contracts were all about how you move data around, utilizing staff, delivering data to an analyst as opposed to requiring very expensive and hard to retain analysts to go out into the plant and collect data and do the work. Over the course of those years, as Robin pointed out, I've led our tech support team, I've led our training department, I've led marketing for some time, and most recently, the last 8 years or so, all of product management. If you're not familiar with where we kind of fit in, we are part of Fluke Reliability, which is a Fortive company. And Fluke Reliability is comprised of 3 main components. So this is Proof Technic. So these are all of our world-class hardware, diagnostic instrumentation, data collectors, alignment tools, balancing applications. This is where we see the majority of how we obtain the data coming from such a powerful product company. And then we tie in between that and eMate, where execution upon results actually defines what needs to get done and how it gets done. We sit in the middle there. We are the software component that has a service arm that can automate those 2 things at scale, bringing data in from a variety of data sources, automating the way that we identify faults, early detection, trendability of how things are progressing, root causes in a very automated way, and pushing that into a maintenance action through eMate. Repairs get completed. You know, there's a lot of Proof Technic hardware out there in order to resolve issues and then validate it again through data that gets captured and automated through our diagnostic engine. Today's agenda is really kind of focused on really where the evolution has taken us and those challenges that now we are facing, and then we'll present a couple of options for some potential solutions to this. Okay, so evolution. This is, I like this slide. This is when I kind of started in the vibration world in the late 80s. We had just transitioned over from what we were used to refer to as the carton cable days. Manual analysis, very engineering constrained, lots of technical knowledge that was required in order to really kind of understand what is really going on with machinery. This is where DLI really kind of got its start. This is on top of an aircraft carrier. That's the ocean right out there. And we would analyze machine data on these ships. It took a couple of weeks to get through about 400 machines. And then we would spend a lot of time going through that data, manual analyzing it, figuring out what could be going wrong with the machine. We would bring all that data back to an office and then write up, type up, using a receptionist would type up all the notes from the engineers that says, hey, these are the faults that we've identified. The DLI model to this, the Azima DLI model, was drastically different than where everybody else was going in the industry. The way that we identified how we would approach analysis, which is still true to how we programmed our software and our automation to support this, proved itself out pretty much right away. And it's a natural order of how things got proven. When we delivered that report, which took some time from the point of which you returned back to the office, went through all that data through FFTs and scopes, identified faults, we wrote it up in a way that identified early detection. This is a unique approach to the way that we were doing it, looking at the data in a way that we could find the very subtle nuances of how a machine might be misbehaving. How do we identify the way that we had identify what is normal and healthy for a machine, and then find every subtle deviation of that was the way that we approached delivering a result. And as such, results came back as faults that were extremely at the early stages, a very slight issue, mostly as a marker for an analyst to start developing a trend, but it also identified the root causes, what is the precursors to how a machine might fail, things that you might be able to steer the course very quickly. We identified then moderate issues, desirable things that you would want to keep an eye on and monitor because they are developing a progressive trend, something that you have many months to take action on. And those became very, very relevant in being able to plan for the faults. And then we had 2 levels of priority actions, things that were serious with an important recommendation and things that were extreme with a mandatory recommendation. You can think of those as things that would last, you'd be okay for maybe weeks to months, and then those that would be extreme that would last maybe days to weeks before you have a catastrophic progression of the fault. When we delivered a report, which took time to get reviewed, typed up, put into the mail, received by the ship that's in the middle of the ocean somewhere, the proof of what we were able to provide was immediately understood. The assets that we said had a extreme issue, those had already failed, and they failed in a way that we had identified that they would fail. The items that we had listed as they had weeks to months, they immediately, which were now in a more serious state given the time, those were immediately taken offline. And those that we identified as being moderate, well, those were the ones that were significantly of interest. Those were the ones that they could plan for, that they knew they had to plan for, because we've proven the ability for us to identify what's going on with the machine. So those became very clear to what needs to happen when we move into today's technology, where all of this is condensed down into a single little wireless vibration device that can provide all of that same technical capabilities. Not just the machine is green, yellow, or red, but very specifically, what are the faults? How long do I have? Can I take action? How do I plan for that repair? There's a technical capability here that plants really struggle with having the know-how to be able to handle something that's very technical, or be able to decipher when it comes from something that is very simplified, but still has a technical capability of it. So the resource constraints that we have can be solved with basically putting sensors on there, but that doesn't handle the technical constraints that then still remain. So that's what we're going to kind of get into quite a bit today. If we look at how things have really kind of progressed, there used to be really fewer machines that needed to be monitored within a plant. They were really more heavy duty, way more industrial. Today, machines have a lot more precision in it, which makes that the technical challenges to do analysis even that much greater. Machines used to operate basically on or off. Sometimes they were slow speed, fast speed, but they would be generally always running, since you had fewer machines that you really were concerned about in a big production plant or factory. But now they are lots of little on-demand variable speed machines. Again, this is something that makes the technical challenges harder, especially when we have more technical constraints with our resources. Though I said before there was fewer machines, more heavy and robust, there was a lot of redundant assets. Plants operated in a way back in the day where you would have big maintenance downtimes, time for the maintenance team to go through and ensure that the machines are operating in the best operational state. And there was redundancy in those. And now plants are operating way more lean, going from kind of short cycles to your 24/7 operations. We've gone from, before those carton cable days, you had the old school analysts that would generally have the screwdriver pressed up against their ear, trying to listen to what's going on with the machine. And that was actually not a human analyst is a very sophisticated analyst if they've been around those machines and understand them, all the nuances. If you look at if you ever look at an old submarine movie, you would see the person who managed those two big diesel engines. That's all they did. They had two machines that they were responsible for, and it was almost like osmosis that they could get up and sense that a bearing needed to be greased, or something might be going wrong that needed to be adjusted. And nowadays, given how lean we operate, it becomes very hard to do that without sophisticated technology. The operators are responsible for a lot more machine. Technicians have to maintain a lot more machines than they did in the past. So we went from the ability to troubleshoot what's going on to a tool that would allow you to say yes or no, this machine is fine, the broadband meters of the 80s, to something where it's a lot more trending, some understanding about how vibration is progressing. Where I see us going currently today is I've talked to different customers about what they're trying to then put into place to handle these constraints, is actually taking that very path and putting it in the reverse direction, where I know I need to have vibration because vibration is a very powerful tool of understanding faults, but I don't have the technical capabilities to really kind of understand high quality, high resolution, very technical data. So I've put into place devices that simplify it, and simplify it to a point where once a light turns red, that my vibration sensor is saying something is wrong, the only way that I can move it forward to understand it is now to troubleshoot. And when we think about from a vibration analysis perspective, troubleshooting is far harder than it is to trend. If I can see a fault progressing in its early stages using a narrowband data, something that requires an analyst to look at, it's easy to identify how fast that's progressing, where it's coming from, and what actions I need to take. But once that machine becomes very problematic, looking at that same data is the hardest, because now you have a lot of things that are going on that's represented in that vibration data. So troubleshooting is one of the most challenging things a vibration analyst can do to figure out what's going on. So then we went to how often data is being captured. In that Navy example that I said, it was annual. They understood that they couldn't wait until the machine was having a problem, since it is a warship as a whole. They needed to have the data captured very frequently. We came on board once a year to look at that data. And what they recognized is when we delivered those results and we said, hey, these machines have a fault that's developing, they immediately recognized somehow they're going to have to get somebody to be able to capture that data more frequently than once a year. And so portable data collectors like this one came out in 1986. This is that same ship moving forward, where technicians and operators would be enabled to be able to capture the data and then deliver that data to an analyst to provide results. So going from collecting data once a quarter, then to collecting data once a month. And nowadays, with sensors in place and the way that plants are operating, data is being captured daily or sometimes more. So if you think about then the challenges that a customer is facing, I need technical knowledge. I have a technical expectation to look at that data. And I used to do it once a month, traditionally, typically for the last several years, to now I'm doing it once a day. So now I have 30 times more data that needs to be analyzed, just further feeding into our resource constraints. And the analyst has also had a bit of a journey. We've had first, there's a lot of certifications that were necessary to get an analyst up to speed. There's several: Mobius, Vive Institute, Tech Associate, has been, and here in the US, domestically, internationally, I'm sure there's several others that are out there that certifies the people that you have on staff. This is a blessing and a curse. Getting that certification, being the level 4 highest level of being advanced understanding of vibration analysis, it's a very marketable job. It's hard for a plant to keep those technical expertise on staff. So you need certifications. Certifications are hard to get, and once they're achieved, it's hard to retain those people within plants. We've gone to lots of machines that operate, tons of data that now coming in. And it's not just the machines data. There's a lot of process data that surrounds what's going on in a plant that is expected of your analytical team to be able to decipher and understand. We've dumbed down the system, in my opinion. We are looking less at the high-end technical vibration that can give you telltale indicators of what's going on. As I've just mentioned before, we're moving backwards in that path to just say, hey, I have a go, no-go situation on a machine. And then there's just the staff itself. There's a lot cost of training staff and keep them retained is a huge challenge. Staffing resources have really kind of declined. The asset count has increased. And those two things are making it very, very impossible for plants to kind of operate. There's a huge evolution here that we're going to try to solve. More machine data and more machines, but you now have less analyst capacity. There is more frequent data coming in, and more frequent data doesn't necessarily mean you have better results. I've asked this question many times in different talks, where a plant is saying, hey, I just need to have, having data once a month is not good enough. I need to have data at least once a day. Now, once a day is not good enough. I need it to be once an hour. And the question is that, do you gain more analytical capability by having more frequent data? And in the way that data is being captured in order to handle this frequency, it's definitely not a direct relationship. A machine, a simple sensor that is not capturing that high resolution data is just blind to the way that different machines can fail. So more frequent data doesn't necessarily mean that you're going to get more analysis. New machines, significantly harder. We're simplifying to the detriment of risking understanding what is happening within production. And as I just mentioned, harder to retain the staff that we have. A couple of numbers I'm just going to throw out here. I thought these were really fascinating as we were researching what the challenge is. And I did this as one of the questions I would get as we're talking through this is, I don't necessarily see it. I hear about it, or I'm feeling like we're just overworked, but I don't really understand how big of an impact there's going to be. And there's a lot of concern here. There's a lot of studies that are out that are really kind of helping us prepare and understand what we might be facing as we move forward. How much of the production staff is going to be not available? How much more production are we expected to get? How many jobs are just naturally going to be lost? The number of manufacturing jobs, 4.6 million jobs will need to be filled between 2018 and 2028, where we're currently sitting right now. How many, and these are skilled labor jobs. There's such a progression of workforce that is set to retire, that we have a gap in how many people we have available to fill those jobs. And the technical challenges that people have are not filling those jobs with other technical resources. Getting people certified and into like a maintenance role is very hard to do with the new generation of people coming out and going through universities and the like. So I thought these were fascinating. 85.2 million jobs in a global talent shortage. It's 54% of the companies. It's $8.5 trillion. This is the number that I thought was most fascinating. 10,000 baby boomers are set to retire every day over the next 19 years. And it's manufacturing jobs. 8 million of those are manufacturing jobs that are going to be unrealized by 2030. Okay, so where does that lead us? One thing that, the kind of clear in those messages is that it's not like we can just all of a sudden have a workforce available to us again. So we have to step back and really kind of think, how do we do things differently? How can we leverage technology today that really kind of prepares us for what's going to come? And it's nice that we know that this is coming. We're in the midst of it now. There's a lot of customers that have reached us saying, hey, this is what we have currently going on. But knowing that this is something that we can solve, I think is going to be very kind of relieving for those that are going to be coming across this here soon. So I broke this down into 3 things that we would really kind of want to define here. How do we capture the data? How do we analyze the data? And how do we kind of really kind of deliver those results? And I first started this with thinking from product management perspective, I have to set this as a set of requirements. And so talking with our different customers, talking with what plants are really kind of facing as challenges, talking with the analytical teams on what they are, what challenges they're facing as well. I came up with some requirements. I broke down the 3 of those into these. So the first one is most definitely data collection has to be super simple, easy to use. If we look at all the resources that you have, it's the technical ones that are the ones that are at the most risk. Having an analyst on staff is the hardest one to retain. But having somebody who's operating, or the technicians that are maintaining machinery in the plant, is an easier solution to have. It's an easier resource to retain. And so as long as the way that data is being captured is super simple and super easy, that Navy model of being able to put it in the hands of technicians and operators, but then transmit that data to wherever an analyst might be, is the way to go. And this supports it has to be able to support a majority of machines within a plant. We're finding where sensors might be placed on machines that are simple machines, but it's not handling those complex machines that are really the bigger risk within an organization. And the more complex the machine, the more analytical capabilities you're going to need. So when we approach data collection, simple and easy to use, but still powerful enough and advanced enough to be able to identify a clear indication of faults and merge all the machines that you have within a plant without adding any additional burden on your staff. There's 2 solutions here I would talk about. And the first one is wireless. And I think wireless is important to talk through because there is just a tremendous amount of conversations about wireless vibration today. And it's a confusing, complicated market. Wireless devices are kind of all over the map. There's a lot of confusion about what you really need or what you gain from different wireless sensors that are out there. I think there's some 250 plus models of wireless devices that are there. So I could break it down kind of simply. If you're thinking about a solution to how you gather more data and to solve this constraint, you need to make sure that that device is still achieving your objective. If you want merely a traffic light that says the machine is red and then you will do something about it, you'll send your maintenance team to just take apart those machines and then go back to a troubleshooting state. And there's certain machines that are certainly fine with that. If you have a lot of a throwaway machine, a traffic light is perfectly fine. You don't need to know what specifically is wrong with the machine if you're just going to throw it away anyway. If it's a more expensive machine, something that you're going to want to repair, then whatever that device that you are putting in place needs to be able to identify that repair for you. It has to have enough resolution in the data that it's capturing, enough capabilities to be able to know the machine is running in a state that can understand the vibration problem. It could take enough vibration data to be able to identify the problem, and it can automate that in a way that it doesn't create a further burden. That the system has to be smart enough to be able to be automated, autonomously sitting on a machine. Things to consider here is how that communicates. You're putting tons of little devices on a machine. How are you going to manage that communication of those? How do you manage the device itself? How does it communicate to wherever you have your diagnostic software? And how do you get results out of that? So a solution to the resource constraints can certainly be simplifying data collection with wireless devices, but there's a lot of questions that you should ask before going down that path. Fundamentally is, what do I need to have out of the program, and is that providing the right answers for you? Most plans try to, if I can't install devices onto every machine, either from wireless vibration sensors or advanced online systems, the simple approach is usually a portable data collector. When you consider portable data collectors to solve this resource constraint, the data collector must be able to not add an additional burden on your staff. Meaning, if the vibration data collector is an advanced instrument, a tool, then there's training and knowledge in order to be able to operate that. That's a certification to be able to go capture data using an advanced device. So thinking through what it is that you really need to have out of this program, when you're considering a portable data collector, think about the simplicity of how do you use the device. Is it built in a way that a technician and operator can capture the data? And is it built in a way that you can then deliver that data to wherever you happen to have analysts? Maybe you have a team of analysts at one plant that you would like to leverage. Maybe you have like a headquarters, a centralized program. Maybe you have contractors that you can use, and you don't want to rely on the contractor to only capture data and the data that they're there. You want to utilize your staff. That's certainly a capability. You want to outsource completely. This is where we have spent a tremendous amount of our Azima DLI talent is in managing vibration programs in this very capacity. Data that comes in from technicians or operators that are enabled to use a portable data collector, and then transmitted to analysts, geographically diverse wherever they happen to be. As we think about the analysts themselves, there are, again, certain requirements that we should be thinking about. And so when I set these out, there are 4 or 5 requirements here that I've defined. Analysts have a huge challenge. When you look at data like you see on the screen here, it's very technical, very challenging to look at this in a way that can define what's really going on in the machine. Analysts have a lot of tools that they can usually leverage in all the different softwares that are out there to try to simplify it and only get through volumes of data as they have to do, and identify just really the big things that need to be resolved. But so when you're thinking about your analyst's requirements, the analyst must be able to scrub through volumes of data, especially as we're moving forward with capturing more data than once a month or once a quarter. That software capability for an analyst must be able to deliver it into a way that they can see prioritized actions, things that are the most important that they need to look at today, and things that they can get to later in the day or tomorrow, or things that they could automate and just say, I don't need to look at this at all. There's no reason why in today's technology of software capabilities that you shouldn't be able to then pass through things that are nice and healthy. A machine that's operating beautifully shouldn't have to consume an analyst's time. So the analyst's requirements are really, I need to be able to understand what's going on, be able to trend early faults, prioritize that list so I know that what I have to look at urgently, be able to have something that automates the screening of that, and it does it in a way that's super intelligent, that can identify this is a fault, this is the confidence in that fault, this is what I really need to do. And we have to do this with a very high utilization rate, given the amount of data that's come in and the constraint of having resources on staff. For us, we look at this from a workflow a progression. We want to be able to set up the devices in a way that feeds into that degree of automation. When we approach vibration analysis, because as I said right at the very beginning, we look at it from the beginning days of when we took on vibration analysis, we looked at it from a different perspective of traditional, as opposed to getting a set of data and then testing the data for various faults. What we do is we've defined what is a normal and healthy criteria of a machine and identify every pattern that deviates from that. And our diagnostic engine then says these are the types of patterns that represent various faults, and this is the priority and the severity of that particular fault. So it's a very automated way, but what requires of that is setting up the system in a way that can enable that automation. So we approach this a little bit differently in setting up an asset, installing sensors and devices, and then training that to say this is a representation of normal and healthy. There is a predefined list of rules and conditions. It's been trained to analyze 1,200 different faults. So the output of this is for an analyst has a ready to go, a prioritized action list that they can work from. These machines have identified as a fault. This is the particular fault. This is the severity of the fault. And all the analyst needs to do is review to make sure that the system is accurate. Not having to analyze the data per se, but review the result that comes out of it and validate if that's true or not. And so it's a great starting point for an analyst to get through volumes and volumes of data. So technology here really is an enabler for a solution to that skill constraint. And just to kind of illustrate that last point here with some numbers, we review this about every year as we take in the count of how many machines that we look at from a services perspective. We analyzed last year about 560,000 machine tests. And from our analysts staff, then we get a utilization rate of what they're capable of doing. And then I have then our direction of how we improve upon our software applications to further enable that utilization. There's a benchmark number that we always start with, which is the industry standard here for if I have an analyst on staff and I'm just bringing in raw vibration data, an analyst needs to look at that data and identify what's wrong and write up a report. An analyst typically can get through about 25 machine tests in a day. That's about the industry standard for what you can kind of expect to do manual analysis on your machinery. We have this automated diagnostic engine that's been, as I said, pre-trained with diagnostic rules. We build a representation of what's normal and healthy. There's a little bit of a learning process here where we analyze data, we further define and refine the tooling, the way that it's going to create accuracy in the data, verify that. So there's a path here, and we build it into a template. So if I have a bunch of machines across multiple plants that are all identical, that template can then be applied to all of those. And then what comes out of this is the system will just automatically generate this automated actionable result that an analyst needs to just kind of look at. And our benchmark here has been for many years about 57 machine tests per analyst per day. So this is where we have been. And now where we've applied really kind of AI into this mix to automate a lot of this refining, filling in gaps, building that template that says it's normal and healthy. The analysts merely need then to certify and lock down that template. They have a workflow management tool that allows them to really kind of see all of those machine tests, those 50,000 some machines that come in, and really kind of automate that with a lot more tooling, such as logic that is persistent. It tells them what the fault was before and how it changed, and confidence to know what needs to be addressed and resolved, and the like. And so our number today has been about 152 machine tests per analyst per day. So about a 5x increase over what is traditional. So this is one way that we can look at, can we apply technology in a way that would help us with this resource constraint? These are tools that analysts that you have on staff could certainly utilize, utilizing software that be able to tell them a prioritized actionable result that they can then turn into an action that somebody needs to do. I wouldn't say that we are at a state where you could remove the analyst altogether. Most plants would not want to operate where you're just relying on this diagnostic engine to spit out that result that says, hey, I have this extreme, I don't know, whatever, imbalance on a machine. The machine needs to be balanced, and somebody's going to make that expensive decision to take down production, take down a plant or a machine to do a repair without having some set of eyes that looked at that data. So from a resource constraints perspective, I'm not suggesting at all that we would remove the resource altogether, but you have to utilize them in a more effective way, that they can look at data, know that they need to look at that data, and have an answer to what the software is telling them they think is wrong, that they can validate very quickly, as opposed to having to scrub through the data to look at it. We present this in a way to an analyst that gives it meaning. So using those diagnostic rules and the templates that's already been pre-trained, having a statistical average of what is normal and healthy, an analyst then gets a list of here's what we think is wrong and why. Here's the severity of that fault and why, and then what needs to be done and how urgently it needs to be accomplished. So it's very easy then for an analyst to be able to say, hey, I need to look at this first. This is what I'm specifically looking at. Do I believe that the system is coming up with the right answer? And they can merely adjust and steer the course. From our analyst team, we do this very meticulously in a way that we track everything that they deviate from what the diagnostic system says, so we can constantly improve upon the accuracy of that system. To relay that accuracy, what our customers generally get is a result that provides them with what is the fault, how problematic is it, what needs to be done, something that they can take action on and assign it to other users, but also comes with a level of confidence. We are highly confident that this fault is accurate, and you have a completion score of how much data you have for those machines to be able to generate that accuracy. So knowing that you need to have a count for how many rotor bars are on the motor gives us more diagnostic capabilities that we're able to identify. So if there's a fault that might impact this, our confidence might then be low, that we think that there's a fault, we'll identify what that is, the end user would see the confidence of that and be able to steer the course. Can we do something else to make sure that we're confident in what that needs to be done. And then of course, everything comes with a level of analysts' commentary so that you can put it all within context. So these are some of the things that we have thought about in the analyst capabilities. Last one here, and then we'll get into some questions, is the requirements for delivering those results. And there are 5 of them here as well. From a tools perspective, it needs to be not just a tool in the box of the maintenance department, which is again hard for a resource to be maintained, but has to have enough visibility higher up within an organization. Things that all key decision makers need to have an understanding about what's going on in the plant. And it has to be translated in a way that makes sense to the business. What is the relevance of this impact or this fault to the impact on production? How much is it going to cost us financially is a really great question to answer. It consumes resources in order to do that. So the requirement here is we need to be able to make this in a way that demonstrates that to different users and aligns with the business as a whole. So we looked at it from a centralized program, putting the system in place that enables us to leverage as much knowledge as we can across different aspects of the business. And we put it in a way that allows us to really kind of build this as an ecosystem, bringing in data from a variety of data sources, leveraging as much knowledge as we can, putting this into an automated system that's backed by AI technology, and then delivering it to users in a way that makes sense, that they can take action on. So limiting the amount of resources that you need to collect the data, limiting the amount of resources that you need to analyze that data, and then getting more people involved so they can make informed decisions. And we can do this with our services as our primary means to be able to handle the immediate requests that customers have to solve this as a problem. All right, so that's it. These are the summaries of what we've talked about today. Collecting data with your existing labor, simplifying the data collector in order to do that. Handling the analysis capabilities by adding technology to automate, giving you a higher utilization rate. Delivering results with higher visibility for all decision makers within an organization. And then if you have additional constraints here, there's certainly services that we can offer to help you reduce that manpower, leverage your asset knowledge across an entire enterprise, adding centralized management to those programs. So it really kind of helps keep these things moving forward. I've left us a few minutes here for questions today. If you have them, they're in the panel on the side, but I will turn this over to Robin. Robin, are there any questions to answer?
We do have some, Michael. Thank you for a great presentation. And to our audience, as Michael said, if you have any questions, now's the time to send them in using the questions section of your GoToWebinar menu panel. And Michael, if you're ready, we'll go ahead and get started.
Yeah, absolutely. Go for it.
The first question is a long one.
Okay.
Here we go. In a maintenance management system process, what is the benefit of gaining that speed in determining abnormalities? Report considering this is mostly concerning rotating equipment alone or some static machines.
Okay, read the question again now that I heard.
Yeah, I knew it was a long one. In a maintenance management system process, what is the benefit of gaining that speed in determining abnormalities? Report considering this is mostly concerning rotating equipment alone or some static machines.
Okay, so when you say speed, I guess my question is, are you talking about the rotational rate of the machine, the nominal running speed of the machine, or are you talking about the speed at which you can actually take data or deliver a result?
There is a follow-up question if you want me to add it now.
Sure.
Do you have a percentage efficiency contributed by this vibration CBM to the entire process of the maintenance management process?
No, okay, so that doesn't seem to be related to the first question.
Okay.
Let me assume that you mean the nominal running speed, and then you can clarify the follow-up question. If we're talking about the nominal running speed of a machine, it's a good point to consider when you're thinking about how you address how you would approach a program. When the running speed of the machine has a very huge impact on the vibration itself. Knowing the operational state of the machine is key to analysis, especially for automated diagnostics, because you want consistency in the data that you're capturing. So the nominal speed, we would, if you're doing a walk around program with a portable data collector, you have a human element to ensure that the machine is running in a stable state. If you have a very advanced online system, an online system has the means of being able to capture that input. If you're using a kind of a wireless device has some challenges there in having a speed input because it's very simple. When that data comes into our system, we try to normalize that data so that we can compare it to what we define as normal and healthy. So the speed value of a machine is paramount in our system. Our algorithms, the way that the data comes through the system, we look at all the different components of a machine and how we can use that to understand what is the actual running speed of the machine. And so if I know, say, number of vanes on a pump or number of teeth on a gear, as well as the fundamental frequency of the shaft that's rotating, I can leverage all of that and say, yep, I know that the machine is running at 25% below the nominal speed or the like. So when we set up a program, we set it as what we think is the normal running speed, the nominal speed that the machine has operated. We'd set kind of a range that surrounds it that says we expect to operate within, say, 10% or the like. We can generally detect the speed pretty accurately to about 35% of nominal. If it's outside of that, if your machine really hunts, it changes speed, is a very varying speed machine, not just variable speed, then those are significant challenge that you certainly have to talk through. So if those are the types of machines you have, we can certainly get into that. Just give us a call and we can talk through different ways to solve that as a problem. Good question though.
The next one is a short question with probably an easy answer.
Okay, thank you.
Is this system compatible with Fluke's e-maintenance?
Great question. So we have a roadmap to bring all of this together. That's the vision of Fluke Reliability. Data from Protectic hardware, automated diagnostics through Azima software, and execution through eMaint. So we are in the roadmap process. We're currently in this process of being able to bridge that gap. So yes, it's certainly coming. And if nothing else, we certainly have APIs capable out of our system that can input into eMaint. But it is in our roadmap to have data and results that come out of the automated diagnostic system feed directly into eMaint.
Well, and that answer actually answered our next question too. So I'll move on to the next question. Any thoughts about the use of checklist?
I need to know kind of what you're thinking there for a checklist.
All right, go ahead. I'll ask that audience member to expand upon that question, and we'll move on to the next question.
Okay.
What types of assets can the wireless sensor cover?
Oh, good question. Yeah, so if you think about what you want to solve with wireless, our approach, and I'll admit here that we only started looking at wireless from Azima's perspective about 4 years ago, even though wireless had been out for about almost a decade before that. Wireless has actually been around for quite some time now. But why it's only now becoming mainstream is the very reason why we only started beginning it a few years ago, is that when we asked our customers what they needed in a wireless program, the fundamental thing was, I'm trying to solve this resource constraint of people collecting data. It's not necessarily that a machine is failing fast enough that I need to have a wireless sensor on the device to catch it. It's just that I don't have the staffing capabilities to walk around and maintain a portable data collector program. And the advanced online systems is way too expensive for all of my machines. So the requirements became anything that I could capture with a portable data collector, I should be able to capture with a wireless sensor. So that's the way I think about it, is that a wireless program should be able to replace your portable program. So the machines that you would have, your critical machines down to your sub-balance of plant machines should be able to look at it with a wireless. The thing that I would caution is that you are putting a very simplified autonomous device in place. So a machine that is not operating for kind of long periods of time, if a machine is very start-stop, extruder as an example is just start-stop, you're relying on a very simplified device to be able to know that, hey, I need to capture the data right now. Immediately I need to capture the data on all the locations on my machine, all simultaneously. And it's a very complicated thing to do. There's devices out there that'll certainly wake up on vibration and capture the data, but it might not be in context with the rest of the locations on the machine. That's a challenge. And lots of machines out there that have varying running states, right? So ramp up, ramp down, this example is very hard to do. So there are some gaps I still see from a wireless device, but I think technology today is getting us into a place that the majority of machines that you would collect with a portable device. So again, that critical, pseudo-critical asset down to your balance plant, sub-balance plant specifically, are capable of a wireless system.
All right, thank you. And I do have an expansion on that previous question about checklist.
Mm-hmm.
Any thoughts about the use of checklist for the process being analyzed?
Okay, so interesting approach here. For us to do analysis, it's not necessarily a checklist per se. There's certain things that an analyst is going to look for to make sure that they have all the relevant information to do analysis. We have what's referred to as a virtual diagnostic center. All of our analysts are use this tool that tells them this is data that's come in, these are all the faults that have been identified by priority, and this is how much time you have to review it per our service level agreement. And it's a pseudo checklist. These are the machines I have to do today. This is the priority of what I have to do. These are the machines that have the most important faults that are, I need to have a turnaround very quickly. These are machines that data has come in that I don't necessarily need to look at. I can purely just automate it. So there's a checklist per se where an analyst can come in and say, this is what I have to do, and check that off the list. There's additions to that where they're also presented with what are the gaps that could be filled to improve upon the accuracy of the system. Checklist per se, make sure I have this, make sure I have this, make sure I have this to be done. Then there's the checklist on the outside of that once we've identified a fault, have we identified the user, notified the plant, talk to the plant manager, get that into program management, trend it, traceability. We have, from our side, we have lots of processes that ensure that these things get done, but we don't necessarily have this as a tool. Every plant tends to operate, from my experience, kind of with their own methods. But we do have, as part of the services that we offer, we do have the ability to coach as well as handle. So if you have a program that you have, say, your own staff, but you want to leverage or utilize them better, how can we apply the Azima model to my own capabilities? If you think of it from a checklist like that I can say, hey, bring us in. We can help. We do what's called a quick start program. We would get everything kind of set up, get the automation kind of defined, get the rules honed and train the staff as we go to be able to say, yep, we've accomplished all these things. Your staff is now has the best foot forward in order to have a very successful program. So there's a lot of flexibility in the way that we can approach this. So I hope that answered the question.
And I know we're at the top of the hour, but can I squeeze one more question in?
Go for it, Robin.
I have some analysts, so they're on site, an on-site program. What happens to them in your solution?
Oh, so that kind of relates to what I just had mentioned, where I have resources, but I don't necessarily want to say, hey, I'm just going to bring in, a contractor and I'm going to displace that. I think there's two things to think about here. One is if you do have analysts, can you use them in a better capacity? And where I see this is removing the mundane. Most analysts consume a lot of their time getting through data collection, that maybe we can solve that, or they have to scrub through all of the data that comes in. How can we automate that to give them a better efficiency utilization? As I mentioned, there's that coaching that we can do, a quick start. Let's add analysts to back your analysts up. We have a lot of these where a plant handles, if you think about it, I have let's say 100 machines in a plant, 10% of them have some significant fault. My analysts can typically handle that. But if all of a sudden they need assistance, we have capabilities of adding analyst capabilities on demand. So coaching to help make sure you're using the system right and have it set up right. But then we do what's called like a second opinion. I'm going to make a recommendation on this very expensive machine that's going to cost the company $1 million an hour to take it down, but I think we need to take it down. I'd love to have a second set of eyes look at that. So our services team has that capability. Data is in our system. We can look at that data with you and provide some guidance. And the last one is there's a lot of things that an analyst can do to really improve upon your process as a whole. Is there a way that you can look at data very specific to your application that might help you build a better process? And most analysts that I've talked to don't have the time to do that because they're consumed in that routine, constant looking at data. So if you think of like our system as an ability to handle those routine tasks with automation, that frees up the fewer analysts that you have. But I think the bottom line is that we never think of this as, hey, you're going to get rid of your analysts for the sake of some other analyst that's going to come in, but how can we bridge a gap or utilize the staff in a more effective way?
All right. Well, thank you, Michael, for another amazing presentation. And to you and our audience, thank you for joining us today. As a quick FYI, when you exit GoToWebinar, there will be a window that pops up with a very brief 30-second survey. We would appreciate your feedback on today's session. Thank you again for joining and have a great day. Thank you, Michael.
You're welcome. Thank you all.